Hi YouTube, this is further paper 2 2008, question 1 hyperbolic calculus, differentiating ln than x. Considering the standard results for differentiating ln functions, then dy dx will be sec squared x over than x. Simplifying further to 1 over sin x cos x and 2 over sin 2x, which gives the proof 2 cosec 2x. Question 2, hyperbolic functions, solving the equation given. So substituting exponential definitions for cos x and sin x, simplifying, multiplying both sides by e to the power x, gives a quadratic, and factorizing gives e to the power x as a half and 6, and x equals ln a half and ln 6. Question 3, integration, to prove the exact value given. From the integral given, if we split the integral, we can see the left-hand side is of the standard results for inverse cos functions. So we can write down the left-hand side as 3 inverse cos 1/3 x. For the right-hand side, considering a substitution, u equals x squared minus 9, and applying gives the square root of u. So then applying between the limits, substituting x squared minus 9 back, and considering the ln definition for inverse cos functions, substituting and evaluating between the limits, simplifies to the proof required. Question 4, hyperbolic functions, curve sketching, to show that the equation of the tangent is this expression in A, and a parallel tangent at Q to find the x-coordinate of Q in B. So considering the standard results for differentiating inverse sin functions, dy dx will be this expression, and given x equals root 2 at the point P for the tangent, substituting gives our gradient. Considering the y coordinate, applying the definition for inverse, ln definition for inverse sin functions, and substituting gives our y coordinate. So applying the straight line formula simplifies to the proof required. So for the parallel tangent at Q, the gradient will be 2. So using our expression for dy dx and solving for 2 gives this expression. So x equals root 2 will be a solution, and x squared minus 2 will be a factor. So applying long division gives 4x4 minus x squared minus 2, and completing the square, ignoring the negative solution, gives x equals root 1 plus root 33 over 8. So the point P, the equation of the tangent, solving for 2. Question 5, reduction formula, e to the power x in nx. To prove In is this expression for n more than or equal to 2 and the exact value of I4. So for part A, applying parts with u equals sin nx. Applying the parts, the left hand side evaluates to 0. And then considering parts again with u equals sin n minus 1 x cos x, and du dx is this expression. Applying parts again, the left hand side evaluates to 0. And then considering an identity for cos squared x, and applying and simplifying, we can see that In is 0 minus n ex sin nx minus n minus 1 ex sin nx plus n minus 1 ex sin n minus 2x, which gives In as this expression, and simplifying simplifies to the proof required. So for the exact value of I4, using the expression from A, substituting n equals 4 gives 12 over 17 I2, and substituting n equals 2 gives 2/5 I0, and considering I0 is e to the power x between pi and 0, then substituting into I2 and substituting into I4 gives the proof required, and applying the exact value direct. Thank you for watching. I'll start question 6 in the next video.